Okay, let's look at more applications of differentiation. And this particular section we will take a look at the Row Theorem and the mean value theorem. Objective is we learn to understand and use the Row Theorem, understand and use the mean value theorem. The first one, let's take a look at Row Theorem. Row Theorem was named after the French mathematician Michael Rolle. And actually Row Theorem renders the existence of an extreme value in a closed interval. Let's take a look at the theorem itself. So the FB continues on a closed interval, square bracket a comma b, and differentiable on an open interval a comma b. If f of a equals f of b, then there is at least one number c in AB that such that f prime of c equals 0, meaning we're looking at the horizontal tangent line. This is important. Differential continues on a closed interval, differentiable on an open interval, and also so three conditions. Continuous on closed interval. Second one, differentiable on open interval AB. And the third thing is f of a equals f of b. And if these three conditions are satisfied, we guarantee there's a horizontal tangent line within the interval. Okay. So from Rowe theorem, you can see that if a function f is continuous on closed interval AB, differentiable on closed interval a comma b, and if f of a equals f of b, there must be at least one x value between a and b at which the graph of f has horizontal tangent right here. This is where the horizontal tangent occurs. F of a equals f of both of equals f of b equals to d. D is a constant. If you look at it, it's continuous everywhere. It's differentiable everywhere within the interval. So that's why we know that that's horizontal tangent occurs, and a horizontal tangent actually is the relative maximum in this case, right? It's because it's concave downward. And also, there's another. I could give you another example. You can see another. If it's concave upward, let's say this is let's say this is A, and that's B. F of B both. This is D. Okay. So as you can see, it's still continuous everywhere. Continuous on closed interval AB, differentiable on open interval AB. and f of a equals f of b equals lowercase d. And we know that you must have a horizontal tangent here. So with that, a horizontal tangent occurring here, and this is horizontal tangent. Which is the relative minima in this case. So if we take off the differentiability requirement from Rolle's theorem, then f will still have a critical number in the open interval a comma b, but it may not yield a horizontal tangent. In this case, this is the case when we have a cusp. Call this cusp. This is a typical cusp, and slope of tangent line does not occur at that point, right? Slope of tangent line does not exist. Okay, but still we have a relative maximum here. Okay, even though there's no horizontal tangent, but we have a relative maximum. Okay. So let's take a look at an example, right? Illustrating Rolle's theorem, find the two intercepts of f of x equals x squared minus 3x plus 2. So this is a second degree polynomial function. We call that quadratic equation. Now it's continuous everywhere. It's differentiable everywhere. So we satisfy first and second conditions. Differentiable continuous. And we just gotta check f of a equals f of b. Okay, so and show that f prime of x equals 0 at some point between the two intercepts. So first of all, we got to figure out the intercept. So setting f of x equals 0, that means x squared minus 3x plus 2 equals 0. Then we factor this using quadratic factoring. We get x minus 2 parentheses times x minus 1 parentheses. The next step is setting x minus 2 equals 0, x minus 1 equals 0. Then adding 2 from both sides of the equation, cancel x equals 2. Adding 1 from both sides of the equation, x equals to 1. So the two intercepts are 1, 2. So basically, let's see what is f of 1. This is f of a. Let's see if it is equals to f of 2. f1 equals 1 squared minus 3 times 1 plus 2 equals 0, right? f of 2 equals to 2 squared minus 3 times 2 plus 2, which is also equal to 0. That means f of 1 equals f of 2. And the third condition is verified. Second condition is differentiable in open interval 1, 2. First condition is continuous in a closed interval 1, 2. So now all three conditions satisfied, right? So we can say that Rolle's theorem apply here. So there must be a horizontal tangent. So in order to find a horizontal tangent, we gotta find out horizontal tangent. We take the derivative. f of x, f prime of x equals to 2x minus 3. Then if you set that equal to 0, then you find horizontal tangent. So 2x minus 3 equals 0, and solve for x. Adding 3 from both sides of the equation, 2x equals 3. Divide 2 from both sides of the equation, x equals 3 over 2. So this is only when horizontal occurs. So, and then 3 over 2 belong to this interval. Right, it's right in the middle of the interval. That means Rolle's theorem applies here, and then that's horizontal tangent. And since this is second degree polynomial, it's concave upward. So concave upward, so we have a relative minimum here, right? Minimum occurs at x equals 3 over 2. Okay. You can take a look at the detailed solutions from your PowerPoint. Now I'm going to show you the graph. This is how after we graph f of x equals x squared minus 3x plus 2. And 1, 0 and 2, 0 are symmetric by the symmetry line, right? And we see a horizontal tangent occurs here. And that yields the minimum. In this case, it's global. It's minimum. All right, it's a global minimum for the whole function. Okay. The next thing, let's take a look at the mean value theorem. And also, people usually abbreviate it as m.v.t. And Rolle's theorem could be used to prove another theorem, which is mean value theorem. If f of is continuous on a closed interval a comma b and differentiable on an open interval a comma b, so there exists a number c in a comma b such that f prime of c equals to fb minus fa over b minus a. Okay, so the slope of tangent line, right? This is slope of tangent line equals to slope of secant line at x equals c. That's how you interpret this. So also two conditions got to satisfy: continuous on closed interval a comma b. Second one, differentiable on the open interval AB. And f prime of c equals fb minus fa over b minus a. Okay, let's use the mean value theorem to finding a tangent line. So given that f of x equals to 5 minus 4 over x, find all values of c in the open interval 1 comma c 1 comma 4 such that f prime of c equals f4 minus f1 over 4 minus 1. So in order to solve for this, right, we got to find the derivative f prime of x. So derivative of 5 is 0. Derivative we just got to find out what is derivative of 4 over x. Okay. So in this case, we got to use the quotient rule, right? F of g is f prime of g minus fg prime over g squared. So let's take a look at the derivative of 4 over x. Put negative sign in front. F is 4, so f prime is 0. G is x, so g prime is equals to 1. I'm just apply the the quotient of f prime, which is 0, times g, which is x, minus f, which is 4, times g prime, which is 1, over g squared, which is x squared. So now, as you can see, f prime of x becomes, this is 0, negative 4 becomes 4 over x squared. Okay, so that's our derivative. And then just basically, next step, find out what is f of 4 minus f of 1. F of 4 equals 5 minus 4 over 4, which is 5 minus 1 gives us 4. F of 1 equals to 5 minus 4 over 1, which is 5 minus 4, which is 1. So f of 4 minus f of 1 over 4 minus 1 give us 4 minus 1 over 4 minus 1 give us 1. And the very last step is just gotta, so this is right hand side, right, this side. F prime of c equals 4 over x squared, set that equals to 1. Then we end up with x squared equals to 4. We cross multiply, so in that case x equals plus minus 2. So that means, however, we're gonna take out, the only thing satisfied will be x equals 2, right? This is the only number within the interval 1, 4, right? So x equals 2 is the correct answer. And same thing as c equals 2. Okay. You can take a look at detailed solutions. I just want to show you the graph. When you graph it, it looks like this. So the tangent line, slope of tangent line, it's right here, right? This is the slope, equals slope of secant line passing through these 2 points. And this is the essence of the mean value theorem, m comma v comma t. Okay. The tangent line at 2, 3 is parallel to the secant line through 1, 1 and 4, 4. Right. The slope equal to each other. When they are parallel, so slope equal to each other. Slope of tangent line. At x equals 2 equals to slope of tangent line, slope of secant line passing through 1, 1 and 4, 4, as indicated from the graph, right? That's pretty much it.